This video is going to be about elastic potential energy, another type of energy. But before we talk about elastic potential energy, we need to talk about a property of springs, because elastic potential energy is all about springs. I'm going to give you two new variables. The first variable is delta x. This means the displacement of a spring from its natural length. And the other variable is Fs. This is the force applied by a spring on an object. So this is the spring force. The spring force always points towards a spring's natural length position. So I'm going to show you what that means. Every single spring with an object attached to the end has some natural length where it naturally moves to if there's no force applying to the spring at all. It just naturally comes to rest at some central spot of the spring. You only experience a force from a spring if you stretch it or compress it away from its natural position. So right here, at its natural position, we would say that the stretch of the spring, the displacement of the spring, is equal to 0 meters. And here, because the spring isn't being stretched or compressed at all, the force that the spring is itself applying is also equal to 0 newtons. This vector shows you how far the spring has been compressed away from its starting position. So the length of that vector is delta x. It's the displacement of the spring away from its natural length. And the force that the spring applies on the object always points back towards the central position, which makes sense. If you try to push a spring in to compress it, the spring naturally pushes against you back towards where it was originally. So these two things always point in opposite directions. If you displace a spring in one direction, it pushes back on you in the other direction. And if you displace it more, it's going to push with more force back. If you stretch a spring out, it's still being displaced, just in the other direction, so that means that you're going to experience a force on the object pushing back toward the center in the opposite direction of the displacement, like this. The next piece of information I need you to know is lowercase k. This is called a spring constant. A spring constant is a measurement of the force that the spring applies per meter that it's stretched. The equation for the spring constant is k, the constant, is equal to the force that the spring applies over delta x, the stretch or compression of the spring. And the units of that are newtons per meter. So every spring has its own k constant. The smaller the spring constant of the spring, the weaker the spring is, the less able it is to apply force. So if you have a spring that has a k constant of 20, that means that for every 1 meter that you stretch or compress it, it applies 20 newtons of force. So if you compress it for 3 meters, it will apply 60 newtons of force. So that's what the k constant tells you. This is related to Hooke's law, which is going to be important for understanding this topic. Hooke's law says that the force from a spring is equal to the negative k constant times delta x. The reason why it's negative is only because the force always points in the opposite direction of the displacement. So if the displacement is positive, we need something to switch the sign to make the force negative, so we multiply it by a negative. And if delta x is negative, we just multiply it by a negative to make a positive force. So that's the only reason why the negative exists in Hooke's law. So Hooke's law says that if you displace a spring by this far, it's going to put exactly this much force, negative k times delta x, back in the other direction toward the center. Here's a quick example of using Hooke's law. A 5 centimeter spring with a spring constant of 200 newton meters is stretched to 8 centimeters. What force does it apply? So if this is the natural stretch of the spring at 5, that's its natural real length, and it's stretched to 8, the actual stretch of the spring is 3 centimeters. So the displacement of the spring is 3 centimeters, which we usually convert to meters when we're working with force. That's 0.03 meters. And we know that the k constant is 200 newtons per meter. So that means that the force that the spring is going to apply at this point is equal to 200 newtons per meter times 0.03 meters, which is equal to 6 newtons. Okay, so you now have enough information to talk about elastic potential energy. Elastic potential energy is the energy stored in a spring that has been stretched or compressed from its natural length. When the spring is released, it will apply a force for a displacement until it returns to its natural length. So it has the potential to do work. It has the potential to apply a force for a displacement, so it has energy. The variable is a little confusing because the variable for elastic potential energy in your IB textbook is the same as the variable for gravitational potential energy. They're both EP. I might replace it throughout the course with EEP, elastic potential, or ESP, spring potential. All three of those work fine, but on the IB test itself, it's just going to be EP. The unit for elastic potential energy is also joules, because everything in energy is measured in joules. So just to visualize what happens when this spring is released, as it begins to be displaced, the spring is applying a force on it, but it's applying less and less force as the object gets closer and closer to the center. By the time it hits the center, there's no force left, and the spring stops applying force. So it can only do that much work. So if elastic potential energy is based on a spring's stretch and strength, there must be an equation for a spring's elastic potential energy that only uses the stretch and the spring constant K. But we have a problem here. We can't use work is equal to force times displacement to calculate the work done by the spring, because the force is constantly changing here. The force isn't constant. The force is getting smaller and smaller until it gets back to the spring's natural rest point, and then it hits zero. So we can't use work equals force times displacement because we don't have a single consistent force to plug into that equation. So the way that we're going to solve this is to make a force displacement graph to find the work done. So I'm going to explain why in just a moment. I'm just going to need you to follow along. This is probably the most complex proof in this unit. I'm just going to need you to follow along with the visual for a minute. So if the spring is stretched by this much, by delta x, that delta x is going to be the displacement that the object starts away from zero. That's how far it is away from zero at the beginning. And the total force that the spring is applying at that exact point by Hooke's law is equal to negative k times delta x. Here I'm going to consider that to just be positive, just to make the graph a little simpler, and I'll consider that to be positive k times delta x. So I'm going to put a dot on my graph. I know that when the spring is displaced this much by delta x, the force experienced is k times delta x. I also know that when the spring is back at its zero position, at its rest position, the total force supplied is also zero, because there's no displacement, so by Hooke's law there's no force either. So at 0 meters of displacement from the center, there's going to be no force on the spring, so I can put another dot there on my graph. So now I just need to decide what the middle part of this graph looks like. Is it going to be a straight line, or is it going to be a curve? Well, I know that the relationship between force and displacement looks like this. Force is equal to k times delta x. And you'll notice that that's modeling a linear equation, where force is on the y-axis, delta x is on the x-axis, and k is the slope, and there's no y-intercept. So if you graph the force from a spring over the displacement, it produces a linear line with a slope of k and y-intercept of 0 newton. So we already decided that the y-intercept makes sense as 0 because at 0 meters it's not supplying any force to the object. So this is going to be a straight linear line with a slope of k. So that's what the graph looks like. Okay, this is something we haven't gone over in detail yet, but the area under the curve of a force displacement graph is equal to the work done by the force. This makes sense because the y-axis is measuring force and the x-axis is measuring displacement. So if you're finding the area made up of one side of force and one side of displacement, you're multiplying those two things together in some way, and when you multiply force and displacement together, you get work as a result. So the area under the curve of this graph is equal to the work done by the spring. So if we can figure out what that total work it can do is as a result of its initial displacement delta x, then we'll have an equation for the elastic potential energy of the spring. So just to visualize it, this is what doing that work looks like over time. It starts with a lot of work, but as it gets closer to zero, it's applying less force over the same amount of displacement. So that means that it's doing less work as it gets closer and closer to zero. So because work is the area, and that area is the area of a triangle, which I know is equal to 1/2 base times height, I can see that the base of this triangle is equal to delta x, and the height is equal to k times delta x. So I'm going to plug those in to base times height, and when I multiply that out, I get 1/2 times k times delta x squared. And that is equal to the equation for elastic potential energy. So the total potential an object has as a result of being stretched on a spring is equal to 1/2 times the spring constant times the stretch of the spring squared. So using this equation, I'm going to solve a few problems. A spring of spring constant 50 newtons per meter is stretched 20 centimeters from its natural position. What is its total elastic potential energy? So I know the k constant is 50 newtons per meter and delta x is 20 centimeters. And you always want to convert centimeters into meters when you're doing this because you're dealing with other things like energy and force that are dependent on meters. So plugging this in, the elastic potential energy is 1/2 kx squared. So when I plug these numbers in, I get a total potential energy of 0.01 joules. Pretty small, it makes sense. This is a pretty small displacement with a pretty normal amount of spring constant. Here's another example. A spring of K equals 200 newtons per meter is already stretched by 3 meters from its natural position. How much work would be required to stretch it to 5 meters? So I know the K constant and the initial stretch and the final stretch, so I'm going to write those there. I'm now going to calculate the initial potential energy and the final potential energy of the spring. So the initial potential is 900 joules and the final is 2,500 joules if I plug those numbers in. So right away you'll notice that the stretch being squared is making the change in stretch matter quite a bit. Like 2,500 is much bigger than 900, even though the stretch didn't even double. So I know that the work done is equal to the change in energy. The work required to move this spring from 3 to 5 is equal to the change in energy that we give to the spring. So here, because it went from 900 joules to 2,500 joules, the change in energy is 1,600 joules. So that's equal to the work done on the spring. So that's how you deal with elastic potential energy.